Good afternoon, ladies and gentlemen. I'm Aniket from EDS Technologies, and I will be your host for today's webinar. First of all, we thank you for taking out time and joining this webinar. This webinar is jointly hosted by ATIRA, Ahmedabad Textile Industry Research Association, Center of Excellence for Composites, and EDS Technologies. Firstly, I would like to give a brief introduction about EDS Technologies. EDS Technologies was incorporated in 1994, and we are the largest technology solution provider in India. We have served more than 2,000 customers and operate across 11 locations in India. We have various strategic partnerships with world leaders in technology space like Dassault System for design simulation solutions, EOS and Optomec for additive manufacturing requirements, Humanetics for ergonomic solution for automotive and aerospace industries, Technia for ensuring product data quality, for multi simulations and training needs of for multi simulations and training needs of aerospace and defense industry, we have Mac technology, SLN technology, and AGM for visual simulations. We also have a strategic partnership with Esri for GIS and location analytics. With respect to EDA, we closely work with Synopsys. We have a dedicated sales, marketing, and customer satisfaction team to address customers' PLM business and support requirement. So before we start with our presentation, I would like to give a short introduction of our today's speakers. So we have Dr. Ankush Sharma from ATIRA. Dr. Ankush Sharma is a senior scientific officer at Center of Excellence for Composite at ATIRA Ahmedabad with PhD in composite materials from MNIT Jaipur. He has published over 30 research articles, authored 3 books chapters, and edited 2 books for international publishers. His work includes filing 2 patents and successfully transferring a technology to the industry. He received the ITSR Foundation Best Research Award in 2020 for his contributions to the field. Then our second speaker is Mr. Srikumar Maganti. Srikumar Maganti is a Senior General Manager at EDS Technologies. He carries a rich experience of more than 20 years in the field of PLM, 3D experience platform. He holds more. He carries a rich experience of more than 23 years working with automotive, aerospace, energy, and industrial equipment segments involving design, simulation, manufacturing, and PLM application. He has engaged and led multiple teams in technology, pre-sales, technical support, corporate training, and customer relationship management. He has worked on-site for numerous prestigious clients to provide the best customer experience. At EDS Technologies, he handled the 3D Experience brand. He also holds various global certificates from Dassault Systems. Then our next speaker is, final speaker is Dr. Aditya Deshpande. Dr. Aditya Deshpande is currently working as a solution consultant for SIMULIA at EDS Technologies. He holds a PhD in aerospace engineering from IIT Kharagpur and has over 12 years of experience in finite element analysis of engineering structures. His expertise include mechanics and damage modeling of composite structure along with advanced simulation technique for structural analysis. Okay, now we will move to our technical presentation. So our first technical presentation would be given by Dr. Ankush.
Okay, so first of all, good afternoon to all. Is my screen visible to all? Aniket,
yes.
Okay.
Can you switch on your camera? Your camera is switched off actually.
Yeah, actually, for the better bandwidth, I just switch off. So now it is.
Okay.
So what I'll do, like during the presentation, I'll just switch off my camera, and after that, immediately I can start. Right?
Sure.
Okay. Yeah. Thank you. So good afternoon to all, and welcome to all on this webinar on the design and simulation for the composite industries. So first, I'm just starting from here. So basically, ATIRA, so ATIRA is Ahmedabad Textile Industry Research Association, established in the year of 1947 by Dr. Vikram Sarabhai, Kastulal Bhai, and the Shanti Sarup. And we have been declared as a center of excellence for the composite in the year of 2011 by the Ministry of Textiles. We are working in a different domains, different focus areas, where the R&D, research and development in the field of the composite, skill development, incubation, and the industry integration. Now, our today's topic is focusing on the composite material, or the role of the design and simulation into the composite industry. So, as you all know, that what is the basic fundamental of the composite. So, when the two materials which are distinct into the physical property, or which are completely of different properties, and we are combining these two or more than two materials and making a single material, so that will be considered as a composite material, where we are getting the combined property of these constituents. There are so many examples of the composite. Some of the common examples are already like mentioned over here. So like fiber reinforced composite, ceramic composite, or the flesh in your leg reinforced with the bones, or like RCC structure. So these are the basic examples of the composite material. Now, so once, like here we are talking about the design and the simulation. So like once we are talking about the design, so there is a more important than any one new application, the new material conception. So see, there are now the world is moving towards the or shifting towards a new paradigm about the material. Now this paradigm is shifting from substance to the structure, similarly from artisan to the science, from workshop to the mathematical modeling, where actually the design and simulation plays a wide role. Then from nature provided to the what man can accomplish. So these are the main parameters where the word, basically the composite material, is moving or shifting. There are so many application of the composite material. Some of the composite common composite applications, along with the competitive materials, and the segments are so aerospace, transportation, wind energy, constructions, pipe and tank, electrical and electronics, consumer goods, marines. So these are the common, or the, I can say, the major application area where the composite has been like used instead of this conventional material. If we talk about the opportunity, so definitely the composite market in India is growing, and the business news said that like as per the CAGR, it is going to be increased by 7.8% over the next 6 years to reach the 2.8. Composite area, composite market into the India is increasing, where new possibilities are there, and how this actually this design and simulation role plays a pivot role into the composite sector. Like if we talk about the common manufacturing processes, so as you all know that there are so many composite manufacturing processes, but these are the very commonly used composite manufacturing processes in industries. So hand layer process, RTM, vacuum infusion, perfusion, compression molding, and subsequently the benefit, or where this kind of the what kind of the particular method can be used for the development of composite material is mentioned. So likewise, hand layering is suitable for the large and complex shape, and subsequently it is a low cost. Where if you talk about the RTM, it is suitable for the medium to high volume fraction, and which is having the high fiber to resin ratio, and especially for the automotive or the aerospace components. Similarly, vacuum infusion, that is suitable for the producing the large or the complex geometry, where also we can achieve the high fiber volume, and that can be widely used for this painter and blades, boat hulls, and automotive components. Perfusion for the building and construction, compression molding for the automotive component, structural component, and electrical and electronics industries. Now, if we talk about the role of design and simulation to composite industry, so composite material revolutionizing the industry with their strength to weight ratio. And in this era, like as the world is moving toward the digitization, so the digital transformation, simulation driven design play a pivotal role in optimizing the material performance, reducing cost, and accelerating the prototype. See, ultimately, the design and simulation helps to select right material, right manufacturing process in order to be achieve the desired structural integrity of your company. So by leveraging this kind of the computational tool, industry can predict structural integrity, manufacturing challenge, and the product life cycle, ensuring the robust and the innovative composite solution. So there are basically two areas. So design can be separate and simulation can be separate out. So design is basically the selection of the material or the design of the material, design of the material properties, design of complex geometry, and simulation. That means you can actually perform you can apply the boundary condition, you can apply the required conditions on that, and you can see how actually your material is behaving under such conditions. So there are different kind of the simulations. Like if you talk about the mechanical simulation, where actually we are evaluating or predicting the mechanical properties of their composite. Thermal, where actually you are conducting the thermal analysis of on your material. Then material distribution simulation, where how you are aligning your fibers, how the material flow will be takes place. So it is more relevant to the manufacturing simulation kind of things. And obviously with this you can also optimize the cost and time of your product development. There are so many benefits that we can say with this design and simulation tool. So design optimization, you can do the complete optimization by using this design and simulation tools. Performance prediction, cost and efficiency, understand the complex composite behavior, process optimization, safety and compliances, accelerating the innovative new product development, virtual testing. So with this now, if I talk about the composite material, which is completely heterogeneous and isotopic material, where we need to be predict the property, or we need to be understand the property of the composite material, so what kind of the loading will be there and how your material will be behave under those conditions. So it is not possible to be like evaluate your material experimentally, or you need to be develop, like you need to be manufacture the material and then you how to be perform the test under the actual condition. Rather than that, if we have this design and simulation tool, so by having this tool, we can actually predict the behavior, we can define the boundary condition, we can simulate the material under those conditions, and without without investing so much cost on that, or in a short period of time, we can actually predict the behavior of your material base, which is helpful to select the right material for your component. Now, ATIRA is also expanding the feasibility, and then we are also there in the design and simulation. So for right now, we are doing the design and simulation for our tools and the product design. Also, we are serving to the industry for such kind of the things. Here, I'm going to discuss some of the case studies where actually like how to predict, or how this design and simulation actually help us to predict the behavior of the material. So first is related to the erosion behavior. So erosion basically, like when I can take the example of wind turbine blade, where the sand particle actually striking over the surface, and with this sand particle there is a deterioration into the material. So this is a test setup where actually the test can be conducted, and here we have the feasibility to put here a specimen or the sample at the certain angles at the interval of 15 degrees. So these are the conditions that has been kept in order to be simulate the behavior, erosion behavior of the material. And this is the place where I can put my sample, and then like the same particle with a certain velocity and acceleration can be strike over the surface. So how this like environment will be created using the simulation tool. So first, like these are the some like the process flow chart, how it will be performed. So first we need to be create the geometry, then we need to be define the boundary condition, then obviously we have to be use certain failure modules, like especially for the erosion behavior, what kind of the failure models are available that can be kept, and then we can visualize or we can predict the results. So here, like first, in order to be have the boundary condition, first we have created the we have created the environment. So like this is my sample, and this is the environment, like which is highlighting by the red color line, and then near to the surface of my sample, that meshing has been done. So the meshing has been done in order to like how we wanted to predict the like uh, evaluate the results. So near to the surface, which is the fine mesh, then little bit porous mesh, and the area near to the nasal, which is the less effective zone of my component or the product. So that will be considered more porous in order to be optimize the simulation time. So with this, what we are able to see. So this generally showing the trajectory of that how the sand particle will be strike over the surface at the different angles. So if I just kept the impingement angle at the 15 degrees, so this will be the trajectory of my particle flow. Likewise, at the 90 degrees, this will be like this. Here, in order to be validate the developed model with the experimental results, so here we just perform this analysis using the CFD, and here this will be my particle geometry. This is the velocity diagram, and here I'm able to see that what the scar is generated. So in the actual condition, uh, at certain degree angle, maybe like I can consider the 45-degree angle if my particle is staying over the surface and I'm getting this kind of the scar. So this actual behavior or this exact behavior that we are able to be simulate in the using the software, where we can also observe the similar kind of the behavior, which is validating my model. Yeah, whatever the work, whatever the model has been developed, which is near to the experimental one, and in that way we can predict the actual behavior of my material, that in this particular situation how my material will be behave, how much material removal rate will be takes place, right? So in the same way, for the different in between angle, we have just considered, so at the 30-degree angle, at the 45-degree angle, at the 60-degree angle, at the 75-degree angle, and we are able to see that yeah, my whatever the like particle will be staying over the surface, I'm getting to the nearer to the scar like what I'm getting into the experimental one. And with that, we just compare the experimental data with the this numerical simulated or predicted values, and I'm getting near about 98% accuracy of my model, what has been developed. So in that way, yeah, so in that way, this simulation, with this help of the simulation, what are the restrictions in my experimental one, that I can only measure my erosion rate at the defined angle, which is 15 degree, 30 degree, 45 degree. But in actual condition, the impingement will not be at the specific angle. So by having this kind of the model, now I'm able to predict my erosion behavior at the intermediate angle also. So say for example, if I wanted to be measure my prediction at 20 degree, so I can directly predict that how much mass will be removed from the material, what kind of the failure erosion mechanism will be there. So those all kind of the parameter now I can evaluate using this. Similarly, in the second case study, again I just consider natural fiber composite, where we predicted the fracture behavior of the composite. And here just basically the 3-point bending SEMB failure like has been considered, failure mode has been considered, and this show the process flow, and this is the actual show the boundary condition how it will be take place. This is the meshing which is near to the crack. So we have to be define the mesh near to the crack, or what is my point of uh, attraction of point of concentration. Near to that, I just consider my meshing, fine meshing, and the sample which is or the which where the actual failure will not be takes place, where I can consider the coarse meshing kind of things. And again, like we have just measured with this simulated results, and experimental have been compared, and almost similar kind of the results I'm getting with the slightly deviation from the actual one because of certain constraints condition, like maybe some noise created during the experimental one. So with that, this has been observed. In the same way, again, the third case study, which is related to the hybrid composite, again where we just develop the composite using vacuum injection process, and different combinations has been considered, and with that we also publish one paper on that. Here we actually predict the mechanical here of the mechanical property of the composite in order to see like how my metal will be fell under the mechanical loading. And here with this, like whatever the model has been created, so we just compare with the experimental one, and we are able to see that whatever the metal behavior I'm getting to my experimental one, the same kind of the things I'm able to simulate using this software tools, and I'm able to predict the properties. So this kind of the analysis is again helpful to predict the property of similar kind of the material. Only I need to be change the material properties. Based upon that, I can predict the mechanical performance of the different material. So likewise, like in the impact. So like say, as you can see in my experimental one, so that load striking point where actually it is damaged. So in the same way that once I simulated the same, like by putting the proper boundary condition, even though I'm able to see the damage or that change in color at the strike point. Now, it is also helpful, like whenever we are designing the composite, so it is also helpful to design the tool or the mold for the composite. So here again, one case study where like we have considered one main rail in order to make the composite component. So in order to select the proper material for the tool, uh, like as it is going to be used with the prepay and the vacuum bagging, so we need to be have that certain thermal loading on this. So we just created one comparative analysis, like whether I just go with the aluminum tool or the steel tool, and we see that how much coefficient thermal expansion will be takes place. Based upon that, I am able to be select the proper material for the tool also. So as you can see here we have considered the two material. One is aluminum, second one is steel, and especially if you see the coefficient thermal expansion for that. So I'm getting the less expansion or the more thermal stable material is the steel. Okay, because in this component my tolerance is very low. So whatever the composite I wanted to make, I need a uh, exact part dimension with very like low tolerance. So for that I need to be select a proper material. So in that way we have just considered the two different materials. The analysis has been done more than two materials, but right now I just showing the results for the two materials. So based upon that, we are also able to be select the right material for the composite tooling. So, so here uh, with that, the future for the this composite industry, especially the role of this advanced technology into the composite industry. So one is the digital twinning, which is actually helpful for the real-time monitoring, the predictive maintenance. Nowadays, AI-powered design optimization tools are there, which is also helpful for the faster simulation and automation. Automation, like in terms of the selection of the material, in order to be see the orientation of the material. So directly now the tools has the capability where directly we can see the orientation. We can have the different kind of the things. We can also have that, like earlier, the particle need to be designed separately. But if I have the particulate filled composite, so immediately I can just randomly oriented particle. I can choose using this advanced designing tools. We can do the completely topology optimization, which is again helpful for the generative the design for the ultra lightweight structures, and obviously for the sustainable material also it will be helpful. So with that, design and simulation not just the tool, but it is enables for the next generation composite industry, which helpful, very much helpful for selection of the right tool, right material, right manufacturing process by optimizing the cost and time. So this kind of the tools are very much essential. So with that, thank you. Now I think I request to now Mr. Sri Kumar for his presentation.
Thank you, Dr. Ankush Sharma. It was a nice presentation on introduction on composites and how you have used basically the design and simulation tools effectively to cater to um, the composites materials, as well as how effectively you are able to make use of the simulation tools to understand the material behaviors, and also how you are able to see the end results coming in. So it was a very nice, insightful session, Dr. Ankush Sharma. So I'll be highlighting on how composites we have been using in the industry, and how we have been able to make use of these tools effectively, especially in the manufacturing sector. And also, I'll just minimize this. Yeah. And also, like, how the manufacturing sector is coming out of different manufacturing techniques, basically, like starting from hand layup. For today they have moved to laser projection systems. So this is how the industry has been progressing effectively. And today I'll take you through how the utilization in terms of application using CATIA Composites in my presentation. So Dr. Ankush Sharma has covered the important elements of composites, like how the composite materials are helping the industries again in different sectors, be it transportation, mobility, or aerospace, or even in textile industry, and also in marine and offshore, and many other applications. So that is the thing which he has highlighted, and he has also taken you through some of those composites manufacturing processes, like vacuum process or full precision and so on. And then he has also highlighted how simulation tools have been effectively used in their in their composites design, and how they are able to see the impacts of this design and simulations. So now I will take you through sector by sector, like how we have been using these composites. So under aerospace, if you see, Dassault System solutions have been a de facto standard for composites for many decades, I would say. And today, 90% of the aerospace OEMs, they make use of Dassault Systems CATIA Composites for their designs and manufacturing preparation. So I'll take one or two case studies for aerospace composites, and then I'll move on to another sector under industrial equipment, that is wind turbine engineering, wherein turbine blades are again made of composites. And then I will also take some glance into transportation mobility, where composite usage has been increasing effectively over the years. So if you look at the aerospace composites, there are many business challenges, in terms of, starting from preliminary design to detailed design, and then manufacturing preparation, and also manufacturing export. We see lots of challenges. So basically, users are looking at tools which are basically in a synchronized fashion. Basically, you move from idea to concept to design to simulations, and then you enter into the manufacturing preparation and also the manufacturing export. So for that, we need to have a system, a platform which will synchronize all aspects of composites, materials, and then it will also ensure that any changes that you make in the near future, you are able to adapt them quickly by making use of these tools. So if you look at the preliminary design stage, there could be complexity in terms of geometries, because the surface design has to take care of the ply modeling and also materials selection, and then you may choose the methodologies of designing the composites. It could be manual plies, or it could be zonal methodologies, or grid methodologies which you may use. So we have certain constraints from the design perspective. Then we are taking the same data, design data, into simulation. So this is where again the simulation parameters comes in place. So we look into the loading conditions, the structural, then the composite material wise also we look at the fiber propagation behaviors. We also need to look at all the shrinkage or knot pitch factors from the manufacturing perspective. We need to run through the simulations and understand how this producibility can really happen. So we have some kind of challenges in terms of long cycle times, and also moving from design to simulation phase without losing the data during the exchange. And also we need to look at cost of materials, labor, and tooling. And if you come into manufacturing, yes, there are so many the manufacturing defects that come in. Dr. Ankush Sharma was highlighting on the tear that can happen in the composite materials. He was highlighting through the simulation example, and how to predict these manufacturing issues upfront, so that we can do it right first time in the shop floor. So this is something like there are multiple challenges at multiple design phases, and also at the simulation phase and manufacturing phase. So we need to address all these challenges. At the same time, we need to synchronize all these tools in order to effectively do the change management as well. So this is where Dassault Systems, with their 40 years of experience, they have come out with the tools which are very, very effective for a composites industry in particular. So I'll take you through an example of the fuselage, wherein the grid design methodology has been adopted. and then how these materials have been applied in terms of layer by layer, in terms of plies and laminates, and also the stacking sequence. And then how the same preliminary design is carried out to detailed design, where you do ply sectioning, numerical analysis, core sampling, and all. And then you move on to the validation and testing phase, right? So in the validation and testing phase, definitely, again, you need to come across the challenges of fiber propagation behavior, and then how you are exactly able to predict those fiber propagation behaviors, and also how you are able to see how the ply area which is being laid up is properly done or not. So that is where we look at the simulation tools, and then we enter into manufacturing. We create the ply book basically. So this plybook is nothing but number of drawing sheets. Each drawing sheet having a complete description about the ply material, ply orientation, ply direction, and then the ply area and thickness. Everything is highlighted over there. So I need to have hundreds of plies information coming in the form of plybook, and we also need to export this plybook, you say, in terms of DXF files or DWG files, which are meant for the shop floor for easy reading and execution. And also we need to see how the future, how you are able to going for nesting and cutting operations, or it could be any other something like laser projection systems, or it could be something with respect to compression molding. So we need to look at the manufacturing process and accordingly provide all the inputs coming from the design side. So once I export all my files, then I should be able to seamlessly do the manufacturing without any defects. So the CATIA Composites will cover all these aspects, starting from preliminary design, detailed design, and also validation and testing. Then you enter into manufacturing preparation and export stage. So if you see here, we make use of multiple brand of tools meant for design simulations and manufacturing. We combine the all brands of the Dassault systems, say in terms of CATIA for product design excellence, SIMULIA for realistic simulation applications, and then Delmia for digital manufacturing, doing the manufacturing execution right up front. So we look at all aspects, and then we synchronize all these software tools to ensure that there is a seamless execution happening for the composites industry. So in this example, if you see here, we have started with the grid design, and then we are checking the detailed design analysis, numerical analysis. We are checking the ply sections, and we are also, providing the same feed for the plybook generations. We are checking the producibility analysis, and also we are looking for structural simulations as well as the composite simulations, and then we enter into extraction, plybook extraction. So finally, you see the digital manufacturing, how this hand lathe or laser projection systems are, automated processes which will take these inputs to come out with the right composite component or assembly. So this is how the entire process has been captured in CATIA Composites effectively. So I'll take you through this example here. So here in this case, you can see this is again with respect to aerospace and defense only. If you look at the composite materials, it will exactly the anomaly goes with the textile behavior only. So here we look at initially, if you look at here, we are having uh, the complete ply information here. We are using the grid design approach in CATIA to define the ply information, whether it is ply area or thickness or orientation. It could be in terms of multiple angles, bidirectional, or it could be unidirectional. And also, along with the orientation, we are defining the material. So it could be aluminum, steel, or any carbon fibers, or any other Kevlar materials. So we need to define those materials in this grid design approach. Each grid having number of set of plies along with their thickness, area, and orientation along with the materials. So once I complete this grid design approach, I will be able to see the complete information of all the plies and the stacking sequence also in the CATIA design itself. So in this case, what you see on the screen is like you are seeing the complete numerical analysis sample having all the ply information coming in the form of Excel sheet also. We can even export that into Excel sheet and check. So in this example, we are seeing this the fuselage portion, and we are defining the first we are selecting the surface, we are creating the grid panel selection, we are creating the grid first. So this grid is nothing but the what do you call in xy directions, you are making the discrete elements so that every discrete element will talk about what ply it has. Now we are running through simple structural analysis, and now you can see the ply material which is there being highlighted in terms of ply section. So we also run through the structural simulation tools to understand the real impacts on this because of this composites. We look at the displacements, one mass stresses, pressure distribution. Now this is another important element, what we call producibility analysis. So this will highlight the fiber propagation behavior of a given component here. So you can see the moment you put the seed point over here, you can see whether the fiber propagation is proper or not throughout. So this is how this is going to impact, and by running through producibility analysis for each ply, we are able to predict whether the fiber propagation is proper or not, and whether the ply information is correct or not. So we are able to do the manufacturability analysis here in this CATIA design itself. So once I complete this producibility analysis, then I can go for the manufacturing, export, and preparation. So there are multiple ways of looking into composites manufacturing. So it could be hand layup, or it could be automated layup machines, or it could be the compression molding or pultrusion, or it could be many other ways of doing this composites manufacturing. Now, in this case, we are actually looking at the complete splice definition. We are going to come out with the isoparametric thickness model, which has got all the plies. Now, I have extracted all the plies and their areas from this particular design. Now, I can even connect with the laser projection systems, and we can see how the output is accurate or not. So this is how, if you see right from design phase to simulation phase to manufacturing, preparation, and export, CATIA provides a complete solution for the aerospace industry. So we have several examples, like Airbus today uses CATIA Composites, Boeing, or it could be even Lockheed Martin, or many other players who are in the aerospace industry. They make use of CATIA Composites heavily. So I will move on to another example. From aerospace. Before that, what are those main advantages of using Dassault Systems composite solutions? Now, when I compare with composites with the metal, there are multiple benefits in terms of corrosion resistance or thermal resistance, or it could be high performance, low weight, durability, and also if you look at the unit constructions of the composites, yes, even the 60 maintenance costs are also very much low compared to the regular metals. So that is how you get the benefit, in the aerospace industry today. So there could be many types of processes. It could be wet hand layup, or resin transfer molding technology, or vacuum assisted resin transfer molding, or it could be pultrusions, or robotic preforming, filament binding, even the braiding technology. We have separate roles meant for braiding technologies, tape laying, fiber placement. So all these kinds of manufacturing processes are well addressed. The input that goes from CATIA Composites design to the manufacturing is almost seamless, and it is 100% error free. So that way, the inputs going from a composites design, irrespective of composite processes, is providing the industry the stable solution. So in this example, as I said, the ply sections, whatever that you see that are getting generated automatically. So these ply sections can be, directly fed into the machines for nesting and cutting operations. So that is how CATIA has been providing what you call design and manufacturing, I can say. From the manufacturability perspective, we are looking into all possibilities even before it goes to the shop floor. So I will move into wind turbine engineering. Basically, today you take any wind energy customers, they make use of these composites for wind turbine blades. So in this, if you look at we need to look at the benefits what this particular solution can provide. So we need to look at the cost savings. We need to optimize the product design. We need to look at how much power we can increase in terms of energy generation, electrical energy. So from coming from the wind turbine blade, how to increase the uh, energy generation from this wind turbine blades, that we need to look at. We also need to avoid the risks because in case of wind turbine blades, the design and also it should be it should run without any interceptions, and it should be able to deliver the required power and energy. And again, we need to look at any failures. So how to avoid these failures? Again, that is another important aspect. Then, of course, we should be the first time to market. There are so many wind energy companies in India. Also, we have customers like Senvian Wind Energy, Gamesha, or Sriram Lickner, and then we have several customers who are very much participating today in the wind turbine industry. So if you look at the wind turbine engineering, again, there are multiple aspects that come in. So blades and aerodynamics. Then we have different types of components like gearbox, pitch systems, yaw systems, and structural parts. We have hubs and bed plates, tower, foundation, and electrical systems. So we need to combine all aspects. So for that, Dassault Systems, CATIA provides, the MBSE approach. That is model-based systems engineering approach to take care of all systems and subsystems. So be it mechanical, electrical, electronics, or it could be even hydraulics, pneumatics, and any other control systems. So we need to combine all aspects and see how the overall system is behaving in a real-time environment. So this is where Dassault has been providing a stable solution. So I'll take an example of a simple wind turbine blade here. So maybe I can look at the design aspect here. So this is an example of wind turbine blade, how it is being designed. So here we need to look at the materials first, and then again we need to select the surfaces. Again, using the same grid approach, we should be able to define all the plies and ply sequences here, the laminates. So you can see different types of plies and materials and their orientations. It could be plus or minus 45, 60, or 90, or it could be even any other angles. So we need to again make use of the grid approach for more accurate predictions, and then we should be able to model this wind turbine blade in this way. So this is how the design is being made here, and then you can also run through the simulations. So if you look at from the simulation aspects, the pressure distribution, and also the structural performance, we can on the displacement, we can actually predict all that. Now, right now, using the 3D experience platform approach, we can seamlessly move from CATIA to simulations, design to simulations to manufacturing without leaving the screen. That is very, very important here. The user interface remains same. We can see the complete ply modeling, ply sectioning, and also the complete thickness areas. And then we can represent the same in the simulation as well, and also run through this composite simulation approach. So here is a simple example in terms of displacement of a wind turbine blade, which has run through the simulation here. Suppose if you make any changes in the design, automatically these things are reflected in the simulation workbench also, because the user interface is same. So this is how the ModSim approach, we call it as modeling and simulation approach. This is going to help a lot in terms of the complete wind turbine blade engineering. So from the simulation perspective, yes, we need to look at all possibilities. So again, here we have load calculations, extreme load cases, resonance analysis. We need to look at the structural noise, foundation design, again, multiple components, the hardware in loop. We need to look at the blade aerodynamics, the thermal cooling, and also the lightning strike simulations with respect to wind turbine blade, and also antenna and radar system, basically with respect to electromagnetic radiations. So we need to cover all aspects of wind turbine engineering in terms of simulations, moving from design to simulation here. So in this example, I'm just highlighting how the simulation can be done, for a wind turbine blade in this example. So as you can look into this wind turbine blade industry, again, we need to look at how to position these wind turbine blades in a specific location. And also we need to look at the what you call the wind analysis, basically, because it has to generate consistent electric power. So we need to look at the wind conditions, and we should be in a position to do the wind simulations as well. So here, looking at this, we can cover all aspects of wind turbine blade simulation analysis using our tools, and then we are able to look at the motor, and also how it is impacting. We can see the real-time simulation with respect to wind conditions. We can also see the airflow around the wind turbine blade and while it is moving. Here, the combination of mechanical, electrical, and also the sensor systems will come in. So we need to look at what are the possible failures, and also how to avoid those failures upfront. So this is where we can look at all the simulation from the overall systems perspective. Again, the antenna and radar systems, we need to look at the electromagnetic radiations that generate, and also the what you call this noise and vibrations. So we need to look at trailing edge losses, and also the noise calculations in terms of decibels. So we should be able to accurately predict the overall system in terms of the real-time environment situation. So SIMULIA, along with CATIA from Dassault Systems, it provides the complete solutions for this kind of simulations. And also the same design you can carry forward to shop floor, and you can see the wind turbine blade manufacturing happening in the shop floor in this way. So here we are doing the digital twin model of the complete wind turbine blade. We are creating the digital assets, and we are able to run from the design requirements to component validation to detail verification, and finally the manufacturing. So this is one example of a digital twin what I can highlight with respect to wind turbine engineering. So today, most of the global customers, they make use of CATIA Composites, because traditionally they used to run in Excel sheets. Today, CATIA provides seamless support for the Microsoft Excel sheets, wherein you can export the complete fly information through the Excel sheet. You can also import them. It is a bidirectional associativity which we can provide using CATIA. So that's where many CATIA, many wind turbine customers today, they prefer CATIA because of this seamless connectivity with other applications like Microsoft Excel. So I will also take one more example on composites engineering with respect to transportation mobility. As you can see here, it's a growing segment for the composites utilization. Today, if you see most of those luxury cars segments, you see BMWs or Mercedes-Benz, or Audi or Lamborghini. You find a lot of composite applications coming in. So I'll take one simple example of A, B, and C pillars, which can be made of composites, because this is the one important portion which upholds the entire body or chassis frame of this main frame of the entire car. So we can look at this B pillar and how B pillar can be made use of composite materials, because this is one which is providing the complete stiffness, durability, strength, or whatever you call. So this is an important part of the body in white design. So we are taking care of B pillar here. We are checking the producibility analysis and we are seeing the fiber propagation behavior using some of those advanced algorithms which are part of CATIA Composites. So in this example, we are running through this producibility analysis, checking whether this fiber propagation is proper or not, which are those areas we may have to have cut pieces. We need to define all those cut pieces upfront by making use of this analysis. So once you complete this producibility analysis, you can go for the plybook generation. We can check all kinds of ply shapes, getting automatically generated in this case. So once you complete that, you will see all the ply shapes coming in. You will extract them into plybook, into drawing sheets, and then you are able to generate all those plies along with the complete information. Basically, it is unfolded ply information, ply area, thickness, and material direction, and also the sequence. Everything is highlighted and automatically generated from CATIA. So once we have this, we can provide this to the shop floor, and accordingly, either it is a hand layup or a machine layup, or it could be any other compression molding or pultrusion techniques. Based on those techniques, we can provide the inputs from our end. So this is one example of automotive application that I would like to highlight here. In fact, there is like the percentage of composites utilization in especially in the luxury car segment has been increasing very consistently. So we can even feed our our inputs also to the laser projection systems, checking out the accuracy of this particular manufacturing process, and we can actually run through this virtually, the laser projection systems virtually in the CATIA itself. So this is like moving from design to simulation to manufacturing, and checking the validating at every step. We are able to see how seamlessly CATIA Composites or Dassault Systems solutions have been helping. So here we can even choose multiple types of formats which will go as a direct feed to the machines. So whether it is compression molding, or whether it is laser projection systems, or it could be braiding or pultrusion, or whichever the manufacturing process, we are able to provide the right inputs from our tools. So today customers are looking for complete synchronization between all the aspects of the composites, film design, detail design, simulation, and also the manufacturing, preparation, and export. So this is what we can do using Dassault system solutions in composites domain. So I mean, we have several customers in India who are using this, and you are able to see the benefits of this. We have many Airbus suppliers, like customers like Explio or Infosys, and also like Capgemini. There are several customers, Umlaut, and of course we also have direct customers like Airbus Center of Excellence, Boeing Center of Excellence. They make use of composites heavily, and we support them. We also provide all the composites relevant trainings as well. So the main advantages of composites is that when you are using the systems tools, you are able to design, validate, manage, and optimize all the complex production ready composition parts, and you can reduce the design time to market. You can also optimize the performance and weight by designing in the context of analysis. And also you can do lightweight engineering. You can also do topology optimizations using the same tools, and you can minimize the development cost and also prototyping, avoid the trial and error methods, because traditionally we have been using hand layup in a traditional way with a kind of trial and error approach. We can eliminate all that using these simulation design and simulation tools. And also we are providing the advanced fiber modeling and simulations, basically AFM simulations for the producibility analysis. This is one of those most important characteristics, because if we are able to predict the exact fiber propagation behavior, then we can deal with any kind of issues that can come up later in the shop floor. So we are able to predict them in advance through virtual tools, and we are able to provide the right inputs to the shop floor. So it is not just a tool meant for just running through this, but it is like seamless synchronization between all aspects of composites design, simulation, and manufacturing. So that's what I can highlight now. With respect to this, there are multiple areas. We also work with marine and offshore applications. We have customers like NPOL and many other government organizations. They make use of our composite solutions effectively for their applications, be it boating design or marine and offshore submarine applications, or it could be, as I said, wind energy or aerospace and defense. Even in the space sector also, we also have provided tools to one of the departments in ISRO uh, for the structures department. So we have several customers who are using these composites effectively for many years, and Dassault Systems, with their future in focus, they are able to provide complete synchronization with the latest manufacturing technologies also, and they have been upgrading these composites tools effectively over the last 3 decades. So with this, I conclude the design part from my end. So I will hand over um, the session to simulation to my colleague, Mr. Aditya Deshpande. He will take you through the simulation scenarios in composites. Aditya, are you there? Over to you.
Okay. Thank you so much, Shri Kumar sir. I hope I am audible to everyone and my screen is also visible.
Yeah.
So I'll be just, as my previous speakers have like established the basic information and the scope of our solutions and tools. So I'll be briefly talking about what the simulation capabilities that our portfolio, that is SIMULIA, has. This is the brief overview of my discussion or talk. So coming to the SIMULIA, that is Abaqus multi-physics solver. Basically, it comprises of 4 different modules. They are Abaqus, FESAVE, EyeSight, and Tosca. So in this, on the left-hand side, we have a complete simulation environment, and on the right, we have optimization environment. And these tools cater to all different simulation and optimization needs when it comes to the structural analysis and simulation parts. So in Abaqus, it deals with the geometric modeling, meshing, defining the loads, boundary conditions, etc. In FESAFE, we have fatigue life estimation, factor of safety, and how different critical zones in any structural component are identified. Then we have EyeSight, that is our parametric optimization tool. And another non-parametric optimization that we have is the Tosca. So coming to Abaqus structural simulation, so it basically is world's leading simulation suite for the finite element methods. So in this, we have realistic simulations for finite element as well as the multi-physics problems. It also offers complete solution for a wide spectrum of all industrial applications, may it be transportation, mobility, aerospace, engineering, defense, consumer products, etc. Also, it is able to handle very complex materials, assemblies, different sorts of contacts, and the problems such as failure, fracture, fatigue, durability, etc. It is based on a very high performing architecture, and therefore with the help of these capabilities we can have a very rapid turnaround for this simulation solutions. What are the key strengths of this Abaqus structural simulation? So we can use various preloading effects to generate the virtual solutions. Also, we can model different damage, fracture, and failure modes and get the assessment of the structures for these types of defects and failures. Also, we can model and analyze various contacts and assemblies. Also, we have a very robust explicit dynamic solver, which can perform all sorts of impact, crash, and dynamic simulations. We can define multi-axial strain-based fatigue as well as geometric nonlinearity for the structural components and assemblies. Coming to the manufacturing processes also, we can simulate those as well. And also the material library is offering a very excellent flexibility in terms of incorporating some advanced materials also into the simulation environment. What are the key differentiators for this Abaqus solutions is it can handle various multiphysics problems in the linear and nonlinear regimes. We can also perform coupled physics problems like the structural acoustic, thermal electrical, thermomechanical, etc. Also, we can perform the electromagnetics and SPH methods of the simulation. As we just now discussed, we can model and simulate very complex materials like the rubbers, thermoplastics, some biomedical materials like tissues, etc. Also, the key aspect is the ability of this solution to be able to correctly model, analyze, and simulate the composite structures. We can prepare the model and we can perform the analysis to interpret the result in a very automated manner, and we can also customize the workflow that we work with. Also, we can have the flexible MBD simulations and complex assemblies like the joints in any biomedical simulation or control parameters for any dynamical problems, etc. Also, we have very robust contact failure fracture algorithm and the solution in this package. As we have discussed, we can perform the high performing computations with very little effort, and we can perform very large scale analysis as well. Now coming to the composite analysis with Abaqus SIMULIA. So it offers the tool for designing an analysis of composite materials. Also, as my previous speakers have established, that we can also perform the manufacturing process simulation with the help of this tool. We can perform various damage and failure analysis scenarios. So as Dr. Sharma pointed out, that these materials are highly anisotropic, direction dependent, and establishing a correct failure and damage response is a very critical aspect. So that can also be addressed very efficiently. Also, we can perform some multi-scale modelings for the composite material, right from micro scale to the macro scales. We can include some various environmental effects, hydrothermal effects such as temperature, moisture, humidity, pressure, etc. Also, we have flexibility in terms of integrating the user customizations and the Python for various automation and some customization aspects. And we have optimization capabilities in terms of parametric optimization. Now coming to what different modules and what different analysis that could be performed. So coming to the basic composite simulation, as the previous speakers have pointed out, that in case of laminated composites, we need to define each and every lamina property individually, and the static sequence and the individual constituents at macro, at micro and meso level will affect the overall composite behavior at macro scale. So this is how we can define the individual ply level properties for the composite construction. So when the composite layup for a laminated composite is defined, so this is how the workflow in the Abaqus environment looks like. So here we can define the layup of the individual lamina, and we can define all the properties that are required to perform the structural analysis. Also, we can control how the ply stacking thicknesses, what different angles contribute to the microscopic design. Now coming to the micromechanics aspect, so we can define also the random orientations of short fiber composite inclusive or the embedded fibers at micro scales, and we can also perform the upscaling and downscaling multi-scale approach. We can use it to perform the various analysis right from micro scale to mesoscale to macro scale. Now the similar workflow we have just demonstrated it in this flow chart. So when it comes to the material calibration, we can characterize the fiber matrix response at micro scale using parameterized unit cells or representative volume elements. In terms of textile composite laminate, we can perform the periodic uh, RV analysis, and we can also make use of symmetric boundary condition, periodic boundary conditions to evaluate the individual stiffness matrices. These characteristics or these constitutive properties will then be used for further structural simulation, and also at the macroscopic response level of the composite, we can evaluate the simulation risk. Now coming to another module, that is the wound composite modeler. It is basically used to design, model, simulate the composite overwrap pressure vessels. So COPVs we can model and analyze in this. So we can define various axisymmetric and 3D models with geometric and winding parameter specification. You can also automatically generate direction dependent material properties, orientations, etc. with the help of the homogenization tool that is available with this module. Also, it is very easy to perform the finite element simulation, and we can also generate various post-processing data for various fiber directions, winding sequences for various materials, etc. Now coming to how the workflow will look like. So here we have the layer manager for this WCM modeler, and we will define various wrapping layers for this pressure vessel designing. As we have discussed earlier, it will use the micromechanics at micro scale, and we can define the individual constituent properties for the ply level layer generation, which will then be used for the structural analysis at macro scales. So here we can see that the meshing for various types of materials and layers are being color coded to identify different materials and different element sizes for the various layers inside the pressure vessels. As Dr. Sharma explained in detail how difficult it is to model accurately the failure and damage in case of composite materials. So here in Abaqus, we have various failure criteria available for the composite materials. So those includes the popular Hashin failure criteria, which defines the fiber tension and fiber compression criteria. Also, we can make use of the matrix tension and matrix compression and shear failure criteria. Also, we have a Puck's failure, Saiwu, Sahil, and maximum stress and maximum strain criteria as well. Now coming to how different damages are modeled in Abaqus. So we have a progressive damage model that is used to define the damage evolution for the composites, fiber matrix degradation, and ply level damage for laminated composites. Also, we have continuum damage models available, and on the discrete fracture mechanics approach, we have extended finite element method, cohesive zone methods, and to define the crack analysis techniques, we have VCCT, that is virtual crack closure techniques. Along with this, Abaqus also provides a very flexible option for a user to incorporate their own damage models and damage criteria in the solver, which can then be implemented for the simulation process. Another module that we are going to see in this is C-zone, that is the crushing zone analysis for Abaqus. So it is an add-on capability, and the simulations are explicitly run to predict the material crush behavior. And also we can provide the direction of implementation of the crush for the failure. We can calibrate the coupon test, and we can include that data for microscope, for the macroscopic and the overall heuristical simulation approach for the composite crushing. So this is one typical example of how the C-zone crushing works in Abaqus. So on the bottom of the screen, you can see that the experimental setup is showcasing how the crushing of a plain composite cone is experimentally tested against the animation which is showing the Abaqus simulation. So on the right in the curve, we can have the comparison of experimental versus the numerical solution, and we can see that it is having very good agreement with the experimental data. Now, just to brief everything up and showcase you the capabilities, I will just present some of the global case studies which our customer from the Dassault solution have been doing with the help of Abaqus composite simulation. So we can perform the simulation of honeycomb structures, so in which the face plates and the cores are defined with the different constituent composite materials, and the layer-wise modeling is being performed. And also, we can have various loading scenarios, and the simulation can be performed with the help of Abaqus. Now coming to the aircraft analysis, so this is a cross section of an aircraft wing, and we can perform the structural simulation of this aircraft wing to define all the different geometrical condition, boundary condition, material orientations of the fiber, composite constituents. We can then prepare assembled model of all the individual spars, rib, stringers, skin, everything together, and this assembly will be then subjected to the given loading condition, static, dynamic, gravity, all sorts of loading scenarios we can include, and this will give us the overall estimation of how the structural simulation works in Abaqus. Also, we can perform various buckling analysis of composite structure. So this is a typical example of a composite panel which is subjected to buckling loads, and these are some of the buckling modes which are compared with the experimental data. And as you can see from the comparison that the Abaqus results match excellently well with the experimental estimation of the buckling characteristics for the composite panel. Also, we can perform various wind turbine blade simulations, as my previous speaker, Mr. Srikumar, explained how Dassault solutions are helping the wind turbine sectors and the manufacturers to enable them to perform these sorts of simulations in virtual platform. So Abaqus also offers the similar capabilities in terms of we can perform the structural simulation as well as the fluid structure interaction of these wind turbine blades. Now coming to the microscopic analysis and homogenization, and how we can perform the multi-scale analysis. So this is an example of how we can assess the strength of injection molded composite part, which has short fiber composites embedded inside. So this is a typical bike brake lever, and it is made up of three different short fiber oriented as shown in this illustration. And we can see that the simulation environment has accurately predicted the exact location of the failure, and also the severity of failure could also be captured with the help of this utilization ratio parameters. Now coming to the pressure vessel analysis, so these are some cases which we have showcased here. So how the approach works is for a given material, for the given fiber and matrix composition, we can perform the micromechanical homogenization to generate the layer properties. These properties will then be applied to create the homogenized model for this composite pressure vessel, and we can perform various analysis. So on the bottom of your screen we can see that there are some stress analysis results that we have generated with the help of this solution. Also some of the buckling cases for the composite liners, and also some unbonding of the liner with other layers can also be performed with the help of Abaqus. Now coming to how the failure is modeled in Abaqus. So here we are showcasing an extended finite element approach. So in this we are defining the damage evolution criteria, and how the material will, the crack in the material will propagate and ultimately result in the final rupture of the specimen. So here we have defined the criteria, and the crack, you can see that once the loading reaches the threshold value, it will propagate and break the part in two. This is actually the physical scenario which could be very accurately captured with the help of this simulation tool. Now coming to how we can model the interlaminar debonding or delamination with the help of this VCCT, that is virtual crack closure technique. So we have defined the debonding criteria between these two lamina, and then it is tested in the mode 1 opening analysis, and this is how the interlaminar crack or interlaminar damage will evolve and ultimately result in the separation of the bonds. Also, we can define the decohesion of a thermoplastic butt joint with the help of extended finite element method. We can also include some cohesive models or some cohesive laws in between the joining and joiner material, and we can see that the experimental data here, we can see that the point, the crack path is shown in the path A, B, C, D, E, and which is also captured in the simulated results very accurately. And from the curve, we can also see that the damage initiation point number 2 and the final threshold are also captured very accurately. Also, we have some cases where we can model the ballistic impact or the dynamical loading, how it will, like tear away the composite structure. So this is like how we have defined the composite plate, and a small impactor is impacting on the structure, and we have used the element deletion feature in this to just showcase how when the impactor impacts will create a crater to the structure and ultimately result in the failure. Also, the drone rotor blades, if they are failed, or if they undergo some structural disintegration, or they experience the rupture, so how the failure can be modeled. So this is one typical case study which shows that the drone rotor blade failure can also be modeled with the help of this Abaqus simulation. Now coming to the C zone analysis, that is the crushing zone. So we have seen that earlier, that how we can use this C zone capability to capture the complex crushing phenomena, and this is how almost 1100 kg of mass is impacted with 9 meter per second velocity, and the bottom one is the actual experimental test, and the top one is from the simulation results. So the results are matching very accurately. So just to highlight some of our esteemed customers who are using our capabilities, that is this Abaqus SIMULIA, for their simulations of this composite and other related structural analysis. So we have listed a few, but we have a legacy of more than 2000 customers that we are catering to. So
as we are at the end of our session, so now I would like to thank our speaker, Dr. Dr. Ankush, Dr. Aditya, and Sri Kumar for a very delightful webinar today. I'm very confident it was very helpful for our audience today. I would also like to thank our audience for taking out their time and joining the session. If you have any further related, if you have any queries for this subject matter or any other requirement, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us at any time, and we would be happy to address your queries. Please do keep an eye on our upcoming events for seminars and webinars. You can follow us on our social media platform for the same. Thank you.
Thank you, one and all.
Thank you.
thank you.
Like whatever the queries the audience have, they can share with them there, so we can reply on that. And thank you, EDS, for organizing the webinar. Thank you.
Thank you so
Thanks.
much.
Thank you.